So today I hope I'll be able to show you that when you have a problem that is shock dominated, where you have large shocks that are responsible for producing noise over a relatively small bandwidth, it is possible to make air acoustic predictions using affordable detached eddy simulations as an alternative to other types of computational methods that may be more expensive. The work was supported took place under the Aerotranet 2 Aeronautica Training Network, which was a Marie Curie integrated training network of the European Community's seventh framework program. And due acknowledgement to their funding is given. So this is the context. There is a constant drive towards quieter aircraft. As, for instance, detailed by the document Flight Path 2050, where a target for a reduction of 65% in the perceived noise compared to aircraft flying around in the year 2000 is stated. Now, this is a very challenging target, considering that it involves a reduction of about 15 decibels at all three certification points for aircraft. The way industry is shaping up to this challenge is by introducing new technology. For instance, in here I picked up the UltraFan technology demonstrator being put together. Now, this technology uses, among other devices, the reduction in the fan overall pressure ratio that goes down to about 1.4 in order to generate a lower exit velocity and therefore decrease jet noise. However, when you operate your fan at the design pressure ratio of 1.4 at cruise conditions, you get a under-expanded jet from the secondary flow, and the fully expanded jet Mach number operating that fan at a pressure ratio of 1.4 happens to be 1.12. This gives you an opportunity for generating shock-associated jet noise. There is also other technology that is coming on the horizon that may motivate developing predictive methods and indeed solutions for decreasing shock-associated noise from jets, as shown, for instance, over here. That is supersonic business jets. We don't know yet whether they are going to materialize, but certainly we need to think about putting our methods in place in order to have acceptable takeoff and noise from those type of business jets. So all these drives the following requirements. There is a requirement for a broadband shock-associated predictor for aircraft design across the industry that needs to be affordable and needs to have turnaround times for predictions that are compatible with the accelerated design cycle in industry of design and optimization. So the aim of the present work was to evaluate detached simulations for providing the input data to a Fowlkes-Williams and Hawkins acoustic analogy noise extractor, and to compare the performance of this tool chain for producing shock-associated noise against introducing in the Fowlkes-Williams and Hawkins post-processor predictions from large eddy simulations. The test case on which we tried this process is a coaxial jet test case that was specified in collaboration with our industrial collaborators Airbus, whereby the primary is subsonic and the coaxial is underexpanded. Some model and numerical method details of the detached eddy simulation method. Detached eddy simulation method was formulated by solving the three-dimensional filtered Navier-Stokes equations in Cartesian coordinates. Detached eddy simulations were obtained by the hybridization of the K-epsilon shear stress transport model of Mentor with the one equation subscript scale model of Yoshizawa. As the flow is shock containing, we needed to use a shock-tolerant, robust solver for the prediction of the implicit fluxes, and this is done by the use of an approximate Riemann solver of rho using the min-mod limiter, flux limiter, in order for our schemes to be total variation diminishing. The scheme is time marching, using second-order Runge-Kutta time integration formulated using the low storage version of the scheme. Oops. The computational domain is shown in here. For the purpose of representing the computational domain in this slide, I have selected to change a little bit the aspect ratio. So your axial distance in the actual simulation is much longer. It covers 50 primary jet diameters in the streamwise dimension, so you have a longer aspect ratio with respect to what you see over there. By the end of the 50 jet diameters, all the shock cells have died out. In the radial direction, I have defined a hourglass Fowlkes-Williams and Hawking surface over which the pressure and the normal gradient of pressure is recorded for the purpose of then using the Fowlkes-Williams and Hawking's acoustic analogy post-processor. This is a snapshot of the instantaneous flow field. Close to the nozzle, we use color ISO levels of Mach number to visualize the flow, and the primary jet is shown to be nice and clean, almost shock-free. In the secondary jet, we have alternating high Mach number and low Mach number sequences. This is your shock train. The shear layer that is on the interface between the secondary jet and the ambient medium on the external side, by around about the third shock cell, has undergone or has picked up an adequate level of instability, so to interact with the shock cell train in a substantial way, so that these generate shock-associated jet noise that is propagating both in the upstream and downstream direction, as shown by the gray line pressure levels. Time average results, comparing the results from direct numerical from the detached simulations, that is named as labeled as cosmic, with respect to larger simulations as labeled by ELSA. And in here we are looking at the Mach number profiles in the streamwise direction. In here, in the first cell, we have a good match between amplitude and also position. As far as the cells further downstream, there is a phase shift in your predictions as far as the larger simulations, because the larger simulation generates an additional expansion downstream or predicts an additional expansion downstream of the primary jet. This is, those are spectrograms of near-field power spectral density. In figure A, we have the output from the code ELSA, larger simulations, and this shows you the typical signature or shock-associated noise by this region of high contributions to your pressure fluctuations. The same characteristic can be seen captured reasonably well in the detached simulations, and if you go further away from the jet axis, that signature remains. This is the effect of this particular signature in the far field. So we have extracted the far field directivity using the Fowlkes-Williams and Hawking's acoustic analogy, and the directivity of the dual stream jet is shown onto the right-hand side. The prediction by ELSA using LES as input to the Fowlkes-Williams and Hawking's acoustic analogy is reasonably well aligned with the blue and the red lines. There are implementations that use the detached simulation inputs. We also have run a subsonic single jet test case. It is shown on the left-hand side, and we obtain similarly good overlaps. In conclusion, we've just had a glimpse that the flow in a dual stream jet is very rich in flow structures. It is an interesting flow to analyze, and it has an intense and steady pressure field. Nowadays, with high-performance computing, it is possible to capture significant geometrical details of your nozzles, such as Stagger angle, and this, we have seen, does influence the development of the jet plume. Where you have a problem that is shock-dominated, and the shocks give rise to shock-associated noise that is constrained in bandwidth, detached simulations seem to be an affordable and available technique, as good, perhaps, as larger simulations for industry-type predictions. And the less computational demanding DS, we are talking about turnaround times of about a week, is well, comparable, perhaps, with the LES that took 3 months. Thank you.
Thank you very much, Jan.
So yes, I am Marianne, and today I'm going to talk about how we can better understand the noise generated by a jet, and especially we study the 3D diffraction by a quarter plane. And the outline for this brief talk is that I will give you my motivation, and I will quickly formulate the problem. I will introduce the empiric formula, and finally I'll focus a bit more on the Robin boundary conditions, which is the main interest of our research. So to begin with, I decided to include this picture of a jet where we focus on the turbine of the jet. So this turbine is a counter-rotating operator which uses 2 lines of blades rotating in different directions. So very naively, what happens there in this system is that the first line of blades creates a swirl which hits the second line of blades and creates a sound. So what we want to do is to model the blade, including the tip of the blade, and then to model it by a quarter plane, and then solve the diffraction problem by a quarter plane. By doing so, we hope that we will achieve noise reduction and hopefully less fuel consumption. So, what's the mathematical formulation of the problem? So the governing equation is a Helmholtz equation, and we have boundary conditions. They can be either Dirichlet, Neumann, or Robin. As I said, we focus on the Robin boundary conditions. We have edge and vertex boundary conditions. So this means, of course, that we have finite energy around our edges and vertex, and radiation conditions. So no contributions from infinity. Now, what happens when an incident wave hits a quarter plane? So we have some reflections, but also when the incident wave hits one edge of the quarter plane, it creates a conical wave. And then if we think it as a race, then it travels along the surface of the quarter plane, creating a secondary conical wave. So in the far field, we can write the total far field as a summation of all these components. So incident, reflected, are conical, primary and secondary, and the spherical wave which emanating from the corner. So the nice thing is that the first 6 terms are fully described by using geometrical theory of diffraction. But we don't know how to describe the U spherical, which is the last component. So the good thing is that in the thought field, the spherical component can be written as a product of an outgoing spherical wave times the diffraction coefficient. So ultimately, what we want to do is to find a nice formula for this diffraction coefficient. So here, I directly decided to include, show you the formula for this diffraction coefficient for the Dirichlet case. Of course, there is a big derivation process behind it, but I didn't have time to talk about it. And so in this diffraction coefficient, in this formula, you can see that I'm using these d sigma diffraction coefficients inside the integral. So I didn't introduce these before. So what these are diffraction coefficients, but of a different problem, an auxiliary problem. So instead of incident plane wave, imagine that we are using sources. and we place these sources really close to the edges of the quarter plane. So these sources now create a new field, this sigma function there, which also can be described as a product of outgoing spherical wave times a diffraction coefficient. This sigma, which is included in the formula. So it's very clear that knowing how these functions, these Edge-Green's functions look like is a very important part of our study. So these Edge-Green's functions, of course, come from the Taylor-Green's functions we all know. So we place the source in distance epsilon from the edge. We carefully choose the strength that we want our sources to have. And, of course, because they are tailored to satisfy the boundary conditions. So the Edge-Green's function is the limiting case when the distance is very close to 0. And so I have to mention here, of course, sorry, that this formula is for the Dirichlet case, and it refers only to the x edge. So we have a second formula for the y edge, which looks like this one. So we have two formulas for each boundary condition. And for the Dirichlet and the Neumann cases, it have been derived that the formula looks like this. So I wanted to focus more on the Robin boundary conditions. The method I chose to use for finding how these Edge-Green's functions look like for the Dirichlet-Neumann case was to use method of images and then conformal mappings in order to map in my physical geometry. So I thought that it was a good idea to extend this method and to use a complex image method for the Robin boundary conditions. So what we do in this case is that we solve the half space problem. So imagine that we have a wall and we use our sources. And not only source and a mirror source is used, but also a line of sources. So imagine that this line of sources gives us the Robin contribution. So write the general Green's function as a summation of g plus ag plus this integral. So this integral corresponds to the correction terms, if you wish. And then apply this into the governing equation, which in this case have been reduced to Laplacian, to the Laplace equation, because we're in near field, and of course in the Robin boundary conditions. So then, if we do that, we find a very simple ODE system, and then we can solve to find big A and alpha. So, by doing so, and again applying mapping, the conformal mapping, which is a complex square root, we find that asymptotically, this looks like 1 over square root of rho times sine phi over 2, plus something else. So please ignore the delta function. This is only because this is the 2D case. So by integrating, we can obtain the 3D, how it looks like in 3D space. And in this point, I have to mention that I didn't mention something very important, that under the conformal mapping, in the Dirichlet and Neumann case, the Dirichlet-Neumann boundary conditions stay invariant. But the Robin boundary condition, basically are not invariant. So now the problem that we finally solved is subject to these boundary conditions, where the impedance constant has a dependence on the square root of rho. And this is a problem for us. So in this slide, I include some possible solutions, so how we want to proceed. So first of all, we can apply the complex image method to a different problem. So afterwards, if we apply the mapping, will lead to the boundary conditions that we actually want to solve. It can be, for example, done by introducing one more line of sources, not only horizontally but also vertically, for example, and having a double integral. Also, we can use Mellin transforms, so not use complex image method at all. And in the Mellin space, the Robin boundary condition is simpler and easier to deal with. As well in the separation of variables. So by separating our problem, we introduce a entirely different problem, where the governing equation is different and the Robin boundary conditions are different and simpler, which also can lead to something very, very good. So in more long-term future work, we want to investigate how the impedance constant H, the effect of it in the Robin embedding formula, and of course to derive the spherical version of the embedding formula with the modified Schmidt-Schlier formula, which allows us to apply it computationally. Thank you.
Thank you very much. Any questions?
No?
We have a couple of minutes. Okay, yes?
Thanks. To what extent can you take into account different geometries by using a different conformal map of the Green's function?
Different conformal map. So you mean to what extent of geometries? Can you please?
If you do a wedge with not at right angles.
Yeah, I guess we can do that. But to be honest, I'm working mostly in the quarter plane. So yeah, I guess we can do that, but I cannot actually answer because I've worked only the quarter plane.
Any other questions? Okay, well, thank you, Marianne.
Thank you.
Yeah, thanks very much. So this is some work I've done in Cambridge with my supervisor, Professor Nigel Peake. So I'm going to look at silent owl flight and what we can take away from this and use to reduce trailing edge noise. So noise is a problem. So aircraft noise is a big problem. If you live near an airport, you're well aware of this fact. So essentially, a large chunk of the noise is governed by, is due to air hitting the frame of the aircraft and just bouncing off and making noise. So this is the majority of noise on approach. So people have done great work on reducing engine noise, but the noise due to the aircraft itself is still a problem. This is also a problem with wind turbine blades. So wind farms often have noise limits placed on them, which means when they're spinning too fast, they have to be artificially slowed down, which seems a bit of a waste of the wind turbines. So we want to reduce this airframe noise, and in particular, we want to focus on reducing trailing edge noise. So trailing edge noise is due to turbulence in the boundary layer, interacting with the sharp trailing edge of an airfoil, and scattering to the far field as noise. And since this sharp trailing edge is aerodynamically necessary, it's hard to see how to reduce this without completely ruining the aerodynamics of whichever airfoil we're using. So one way to look at this is to think about owls. So owls are well known for being silent, as per the title. Only large owls are silent, but they rely on this to hunt their prey. They're both not heard by their prey, so their prey doesn't run away, and they can hear their prey because they're not making noise. So because only large owls have this property, most birds of prey are reasonably noisy. It's possible, as some experimentalists have done, to essentially take an owl's wing, take it off the owl, put it in a wind tunnel, and see how loud it is and why it's loud. So we know why owls, well, we know the biological features that owls have on their wings that makes them quiet. So they have a soft downy coating on the upper side of their wing. They have a comb of hooks on the front of their wing, and they have an elastic trailing edge fringe. So the comb of hooks is probably aerodynamic. We're going to ignore that. The other two things are modifications that allow owls to fly quietly. And people have taken these ideas and tried to create devices that mimic these features. So the picture at the top, we have finlets, which are streamlined, orientated objects near the trailing edge of an aerofoil that are aiming in many ways to mimic the soft downy coating on the upside of an owl wing. You can do other things mimicking owls. You can consider serrated trailing edges. There's lots of work on serrated trailing edges. You can consider porous and elastic trailing edges. And as you'll see later in this session, you can also consider active noise control methods. So we want to understand why these methods work. And you can take various measurements, and you can experimentally see that these things reduce noise. They seem pretty good. And we want the mechanism as to why. So the next step is to look at what engineers normally do. So engineers like aim at theory. It's essentially you take measurements of the surface pressure near the trailing edge of an aerofoil, plug this into a Green's function, and use this to compute far-field noise. This is really good from a practical point of view for seeing if your thing you've designed is quiet, but it doesn't actually tell you much about the mechanism behind the noise reduction, considering the noise reduction also is apparent in the reduction in surface pressure fluctuations. So not very useful for what I want to do. So these devices have a large effect on boundary layer shear, as suggested by the title. And there are theories that if we approximate our aerofoil by a flat plate, because we're mathematicians, we can consider a vortex sheet turbulence, approximation to turbulence in the boundary layer, and calculate how noisy it is as it passes over the trailing edge of a plate. So I'm going to look at that in a moment. First of all, I'm going to briefly look at vortex sound models. So in idealized conditions, mainly if we don't have any rotational background flow, we can consider a point vortex moving near an object. So it moves with the background flow, and it has some self-induced motion. So here, the blue trajectory at the top is just a vortex passing a flat plate with some uniform background flow driving it forwards, and its slight dip in trajectory is due to its own interaction with the trailing edge. The orange line is if that cylinder that is shaded was there, the vortex would go up and around it. And on the bottom is a plot of the acoustic sound signature. So in the far field, you end up seeing a cylindrical wave due to these vortices as sound sources. And this is essentially the magnitude of that cylindrical wave. So we see, essentially, you shove a vortex further away from the sharp tip, and it gets quieter, which is unsurprising. The problem is this model is very idealized. It ignores many things. Well, this very specific model ignores a vast amount of things, but even you can make more complicated versions of this model, and it's still idealized. And ideally, we'd want to take something like this that includes large geometry and include boundary layer shear in that problem. So if we don't have geometry, we can just, flash image. This is a point mass source in a boundary layer, essentially generating a vortex sheet behind it. So this is good. So if your boundary condition is streamwise homogeneous, and if your flow, more importantly, is streamwise homogeneous, this is quite straightforward to do. Simple Fourier transform stuff. And you can take it to the next level and consider a trailing edge of a flat plate. So you have a flat plate upstream, you have a wake downstream, and you can use Wiener Hopf to compute the scattered solution. And then you can use that scattered solution to compute the far field noise, entirely controlled by essentially what's happening at the tip. And therefore, you can look at how changing boundary layer shear can change your far field noise. So here we have a reasonably high Mach number flow, I think. And this is showing the directivity of the far field noise. So 0 is downstream. And we can see there is changing the shear affects the direction of this lobe. So there is an effect. The problem with this is it doesn't include geometry. So we saw the vortex sound models earlier, and they have geometry included in them. We had a large cylinder at the end, and we could look at the vortex going around that. We can do similar things with this framework. So essentially, we move to a coordinate system given by the streamlines of some background flow. This background flow is rotational. We're assuming it's sheared, which means we don't have a velocity potential, which will be useful because that will give us a nice orthogonal coordinate system. But we can pretend we do by constructing an orthogonal coordinate system. And this gives us a framework in which our equations from the streamwise homogeneous case we just saw transfer reasonably nicely into a new coordinate system, particularly if we have high-frequency hydrodynamics and acoustics going on. So as an example, I'm going to show you what happens if we have an infinitely shear background flow, which brings into problems of its own, but we'll ignore that, passing over a circular bump that can be reasonably large. So for this problem, you can calculate what the stream function is, assuming there's no recirculation happening, which causes problems. And from this, you can calculate the orthogonal coordinate lines, and you get a nice, pretty coordinate transformation. And the reason for doing this is we saw before that a vortex sheet was excited. And this vortex sheet essentially confines itself to streamlines. So in the new plane, in the top left picture, the vortex sheet remains on a nice flat line, and this generates noise as it's accelerated, as the flow accelerates over the bump. So we transfer back to real space, and we can see that we have a nice amplification of noise as the flow passes over the sphere, the cylinder, for reasons of both acceleration of the flow and increase in proximity to the hard wall. So we can see we can do this coordinate transformation and still do some useful acoustics, or hydrodynamics in this case. And what we really want to do is compute the scattering of this from a trailing edge. And this is helped by noting in this framework, we've assumed that as far as the acoustics is concerned, the background flow is changing slowly, which means we can do most of the far-field noise entirely by doing a scattering problem frozen on the tip, which gives us exactly the same scattering problem as we had before, except with a more complicated, messy background flow. So we've essentially shown we can use previous results in a more complicated case and get useful results out. So in conclusion, essentially we can use a clever coordinate transformation that essentially, in certain approximations, reproduces earlier work. And in certain cases, as the one I've shown, you can get some analytic solutions. And we can see that geometric variations themselves create noise. And further work is to take this sort of thing and to generalize it to just looking at, say, a thick trailing edge. So generalizing the vortex sound models we saw earlier, and hoping that this provides some way of looking at how passive noise control models, passive noise control devices, for example, finlets or the upper surface and outer wing, can reduce background, reduce far-field noise.
Okay. Thank you very much. Any questions? Okay.
So just a quick question for the picture you showed at the beginning of the serration and all these kind of things. It seemed to have a structure in the third dimension.
Yes.
And so obviously what you've shown here is
It's two-dimensional,
So
yep.
how do you
So
take that into account?
there are two ways of looking at it. One, these are very small, so the actual three-dimensional effect on the background flow is reasonably small if you sort of average it in a hand-wavy sense, which is dubious. These models feasibly should be extendable to completely three-dimensional, but it would probably be horrible. So I don't really know how to take into account the three dimensions. Yeah, I don't think it can be directly applied to this sort of thing, directly. Yeah.
Might not be that bad, just do a span-wise integral in some
Yes,
framework.
so I've done some, so for the vortex sound stuff, I've done some equivalent things. And it produces results that work, but it is very hand-wavy.
Okay, well, thank you very much, David.
Thank you.
Afternoon, everyone. My name is Adam Higgins. I'm from the University of Southampton. I'm going to present to you today the work that I've undertaken along with my supervisors, Professor Stephen Turnock, Professor Phil Joseph, and with some help from Dr. Arthur Litker, also at the University of Southampton, into investigating the tip gap flow and its influence on ducted propeller tip gap noise. So the motivation behind my work is a marine application. Submarines, or military vessels in general, but especially submarines, rely on quiet operation to avoid detection. Ducted propellers are widely accepted to reduce the noise, although the actual mechanism behind the noise generation, and therefore the reason why ducted propellers reduce the noise, is not currently very well understood. And so we're going to look into trying to identify the actual noise mechanisms so we can go through a more proactive design process to reduce the noise rather than simply reducing the gap and reducing the noise passively, semi-passively. So to investigate this, I'm going to simplify the kind of the real problem of the ducted propeller down to a single stationary blades, such as this one in the schematic. We have a stationary blade at an angle of attack, and we're going to change the gap between the boundary surface above the tip of the blade and investigate what the effect is on the formation of the vortex. And then at the end, I'll show you some initial far-field noise predictions made using an acoustic analogy by Folks, Williams, and Hawkins. So the initial investigation is this. It's a NACA 0020 foil, used because we have a lot of experimental data at Southampton based on this foil. It gives us quite a nice thick foil to look at, so we have quite separate vortex systems and we can really kind of dig into it. And then we'll investigate what happens when we start adding more realistic features. So initially, the simulations I'll show you have a slippy condition on the boundary. We'll then move to including the no-slip condition on the boundary and see what effect that has, and then moving to a thinner and highly cambered foil to try and get more towards a realistic case. So the initial investigation of the 0020 foil showed this kind of effect for the performance coefficients based on the tip gap height. So we have the tip gap height against chord along the bottom with reducing gap height towards the left. And you can see that the solid line for the lift coefficient increases from quite large tip gap heights, so you get an increase in your performance with regards to lift. Whereas the drag coefficient, we can see, stays fairly constant until you get to really quite small gaps of around 7.5% of the chord, and then it suddenly drops off. So this is kind of what we've identified as a kind of critical gap height. We think that this gap height will be dependent on the geometry of the foil as well as the inclusion of the boundary condition of the no slip on the duct. But it infers at least something that can be done relatively cheaply computationally. We could have a reasonably accurate inference of where the tip gap height might start to influence the actual tip vortex formation. So using a steady RANS approach, we can see the open tip foil on the left-hand side here. You can see two main structures. So we have the pressure side is on the bottom of these figures. The suction side is on the top. The flow is coming from right to left. And so we can see that the first vortex forms over the top of this pressure side edge. And we have another vortex forms over the side of the suction side edge. And as it gets towards the trailing edge, they coalesce and propagate downstream. Now, as we hit that typical gap height of 7.5%, we get what we have on the right-hand side, which is a kind of shearing of this vortex here. So as the gap height is reduced, the tip flow velocity is increased due to the contraction in that region. And so it kind of pushes this vortex through. So we get a shearing of this vortex. So this kind of view here is not really physical. You shouldn't really have holes in your vortex structures like this. So the steady simulations might not be particularly useful once we get to these complex regions. So we move on to more high resolution LES simulations and look at the unsteady features. So we can see that stable looking vortex on the pressure side edge is actually quite unsteady. It's quite a helical structure. And we can see that is getting pushed through the tip gap via the tip gap jet. So it's pushing it through, so it doesn't get all the way to the trailing edge. It gets pushed through instead. Now, I've kind of inferred some potential noise source regions based on this simulation. We've heard previously about trailing edge noise. We know that when you have highly turbulent structures go over a sharp, solid boundary of anything, you will get scattering of these structures within the boundary layer, and that generates quite a lot of noise. So the kind of key regions I've identified initially are the pink one, where we have the vortex forming on the pressure side edge, the green region where you have the more stable vortex, which is forming on the suction side edge, and then the yellow region where the vortex actually sheds over from the pressure side edge, it actually sheds over the suction side edge of the foil. One interesting point to note is with regards to design applications and for industrial applications, actually, if you're looking back at the RANS that we said was not really being strictly physical in this region, it does actually represent quite well what is actually happening in the unsteady case. So this is quite useful from an industrial point of view, in that you can actually use the RANS quite reliably to predict where these large coherent structures are. So what happens when we start including the boundary layer effects? So this is a movie I have to start. So I'm going to talk through it quickly before I press go. So we're going to spin around, trying to give a little bit of context. We're now looking down on the foil, down on the table, sorry. So the boundary mesh is shown in white. We can see that we have this large stable vortex as we saw before, but then because of the no-slip condition, we're starting to generate some kind of counter-rotating vortices near it. We also have horseshoe vortices forming at the front. And inside the gap, we'll go and have a look at that through the course of the video. You'll see that things get a lot more messy in the gap because of all this vorticity very close to a no-slip condition. It whips up more vorticity, and instead of getting that kind of clean helical structure that we saw before, we get something a bit more messy being sucked through. So we'll spin around, have a look down on the tip. So we can see these kind of messy structures in the tip. And we can see these counter-rotating vortices being whipped up by this large primary vortex system. So if we break that down into a schematic, we have the small vortex forming on the pressure side edge, which gets broken down into a kind of sheet of vorticity. It gets pushed through the gap. That sheet of vorticity then drives this large, what I'm calling the primary vortex, which I've labeled C. And then that large vortex then drives counter vortices due to the no-slip condition on the boundary, which I've labeled D here. So I think based on those lines that we were looking at before, the most important one really is going to be this suction side edge where we have highly turbulent structures being shed over a sharp edge. So that's really going to be the region where we expect to be able to make some good gains in terms of reducing the noise. So the next step was to move on to something a bit more realistic, as I said. So this is now a 5510 foil, so it now has camber and is a lot thinner. This is following on from some experimental work by Jacob et al. And so we can see just at the bottom here, you can just about see there's a very small gap between the foil and the table in this experiment. And this is what I've recreated numerically. We can see very similar flow structures to what we saw before. If we look at the top left, we can see, due to the orientation, the colours are actually different now for the vorticity, but this primary vortex is now red here, and then we can see the counter vortex blue, and that is then strong enough to in turn generate another one. These also are driven by the horseshoe vortices, so these all combine and drive each other as they go downstream. Looking into the tip, this is the leading edge of the foil here. This is the trailing edge going vertically down there. So this is the pressure side edge there. And we can see that this vortex is now very, very small. We've gone to a much smaller gap. And it doesn't have the room to generate a large structure anymore. Instead, it rolls over and creates quite a small vortex, and then it's broken down into that sheet of vorticity that I was talking about earlier. So this is shed through the gap and over the suction side edge. And we believe that the noise mechanism associated here is going to be something very similar to that of trailing edge noise. We've then done some pretty preliminary investigations of the far-field noise propagations, just to look at some rough directionality. So we have the domain shown here on the right, just to kind of put everything in perspective. We have a receiver upstream, downstream, to the suction side and the pressure side. And you would expect that the suction side would be slightly noisier, as that is the side that the vortex comes through on. And we can see in the far-field predictions that you do get a little bit more from the suction side than you get from the pressure side. And due to the directionality of the surfaces, assuming a dipole noise source, the suction side and the pressure side are far stronger, far more powerful than those upstream and downstream of the foil. I think that's my time there, so I'm going to leave my summary up just to summarise what I've talked about now. Are there any questions? Thank you.
Any questions?
Just a comment on your second bullet points. When you have a lifting body with camber,
Yeah.
you need to be careful about the photon circulation you're generating versus the noise that you're trained to correlate. By that I mean, imagine your tip gap. I can move my casing away and change the gap, or I can change my span, so my total circulation, the lift changes. So these two effects need to be decoupled. So, and just a comment, really.
Okay.
You need to be careful that when you are changing by chopping off
So the actual coefficient graph, for that one, the span of the 4 stayed the same and the boundary moved.
Correct.
So, yeah, so you're normalizing by the same thing, but yeah, you are changing the size of the pressure domain that you're working with, yeah.
You can do it in 2 different ways.
Yeah.
Okay, right. Well, yeah, I think we're out of time,
Yeah.
actually, so thank you very much.
Thank you.
Hi, so yeah, I'm going to talk about nonlinear acoustics and a non-parallel boundary layer over an acoustic lining. So just a brief outline of my talk. I'll first have a bit of an introduction to explain what some of those things are, talk about the linear acoustics, the nonlinear acoustics, and then some results. So first, why do we care? So engine noise is a major contributor to aircraft noise, in particular the fan inlet and outlet. And manufacturers use acoustic linings to try and reduce the noise inside the duct. So what is the acoustic lining? You can see here it's the, can I get struck? It's the darker region inside this duct. And it typically consists of an array of these Helmholtz resonators, which are cavities with a perforated sheet on top of them. And they're typically characterized by their impedance, Z, which is defined as the acoustic pressure over the acoustic normal velocity. And we'll be assuming a mass spring damper impedance here. So talk about the linear acoustics. So first, I'm going to have cylindrical duct, Navier-Stokes with perfect gas, and I'm going to assume my viscosity and thermal diffusivity depend linearly on the temperature. And I'll have a non-parallel boundary layer flow inside the duct. So first, some scalings. For the boundary layer thickness, we have the typical Blasius boundary layer scalings. And then for the acoustics, to find the length scale over which viscosity affects the acoustics, we consider scaling the time dependence of the acoustics with the viscosity, and we find this length scale lambda depends like the boundary layer thickness divided by the square root of krx, where kr is a characteristic wave number and x is our distance downstream. So we'll define this parameter epsilon k, which is 1 over kr x naught, where x naught is some characteristic distance downstream, and we'll say this is small. So this means we're many wavelengths downstream of the leading edge of our duct, and it means we can neglect the scattering from the leading edge of the duct. So we then get this type of behavior. So in region 3, which is the center of the duct, we have the acoustics acting inviscidly with a essentially uniform background flow. In region 2, the acoustics are still inviscid, but we now have to consider the shear of the boundary layer flow, and then it's only in region 1 where we have to consider viscosity. And then we're going to use a WKB type approximation to solve for the acoustics. And for this talk, I'll just be looking at the leading order acoustics. So in region 3, we have the standard Bessel function type solutions, and we just need to find the function A. And for the leading order case, that'll be a constant. And then I'm going to skip through the maths. We solve in each of the other regions, and we match through using our impedance at the wall, and we find the following dispersion relation. And the first two terms come from the kind of historically used Myers condition, and the last term is the new term from the non-parallel nature of the boundary layer flow. So just to show some results for this, we can look at a point source at some point r0, x0, and invert our Fourier and Laplace transforms for long time to get something like this. So we've got a point source at xc equals 10.1, and you can see the waves here. And although it looks like there's waves coming in from the right, those are actually evanescent decaying waves. It's just because we're at long time, their phase speed goes to the left, but they do decay to the right. So now I'm going to talk about the nonlinear acoustics. So we're going to assume our acoustics are weakly nonlinear. So we can solve first the leading order linear acoustics and then the nonlinear acoustics are a linear system forced by quadratic terms in the leading order acoustics. And I'm going to define capital omega as the sum of the frequencies, capital K as the sum of the wave numbers, and capital M, or curly capital M, as the sum of the azimuthal wave numbers. And when we do this, again, we have to solve in each region. In region 3, we again get a Bessel function type solution, but now we depend on capital omega and capital K instead of just omega and K, and we need to solve for this D. So we solve in each region again. I'll skip through the maths. And we find D has this form, which is nice. We can then invert our transforms. Except we have one problem here. When capital omega is 0, this blows up. And capital omega is 0 corresponds to acoustic streaming, which isn't something we can just ignore because we will get that. So we need to look again at our equations and see what's going wrong when capital omega is 0. And essentially, the main equation we're solving in region 1 is this equation. And when capital omega is not 0, we have a balance between the first term and the last term. But when capital omega is 0, we have the second, third, and fourth term all need to be balanced. And we then get solutions in the form of Airy functions, which we can solve. And assuming exponential decay of the Airy function of the second kind, we get the following type of solution, which is now dependent on our distance downstream. So this is quite nice. We've nearly solved for the nonlinear acoustics. We now just have the one small problem that I said this is only valid if we have exponential decay of the Airy function of the second kind. And in the case where we don't have that, which ends up being that the argument of capital K is minus pi over 2, we find our solutions in region 1 are now oscillatory because this A in the exponential is real and positive. So this oscillates in region 1 into region 2. And now if we just look at the results from parallel flow, so here there's two plots showing in the case of parallel flow where you only have one inner layer. We previously found that in this case, you get this similar oscillatory behavior, and this ends up propagating out into the center of the duct with this streaming mode with a very high frequency, very large acoustic streaming, which is clearly nonsense. So we want to see, does this still happen in the non-parallel case, or are we still missing something? So to check this, we need to now look in region 2, matching this region 1 solution to region 2, which you can do. So you do multiple scales type solution. And the important point is in our G, we have this exponential to the integral of some terms. One is capital V, which is the boundary layer normal velocity. And one is this u zeta over 2x, which is essentially the x variation of our streamwise velocity. So both of those two terms come in from the non-parallel nature of our boundary layer flow, and this exponential causes this oscillatory solution in region 1 to decay exponentially in region 2, so we don't get this spurious acoustic streaming propagating out in the center of the duct, which is nice. So just to show some results for that, so the top solution here is the linear acoustics. The middle solution are the nonlinear acoustics without the streaming terms, and the bottom is the nonlinear streaming terms. And we see here we don't have these rapid oscillations. We just kind of have mainly localized near the wall for the acoustic streaming. And obviously there's some discrepancy along the same line as the source, just because I've truncated my inversion series. And we can also do the same with multiple sources, but that's not too interesting. So to conclude, I've shown that it's necessary to consider the non-parallel effects of the boundary layer for acoustics in flow over acoustic linings. Using this 3-layer asymptotic matching means we can then get analytic results and invert our transforms very easily. And also, I forgot to mention, but the nonlinear acoustics inside the center of the duct end up being amplified by a factor of 1 over delta due to these interactions inside the boundary layer. And for future, I'd like to investigate the well-posedness of this scheme, in particular whether we need to consider the order delta correction which is normally needed. And also, I'd like to consider the effect of variations of duct diameter. So, thank you.
Any questions? Yes, thank you.
You said you're using a Blasius boundary layer.
Yeah, a compressible Blasius boundary layer.
Okay, but you also said that you're many wavelengths downstream of the leading edge.
Yes.
What sort of wavelengths are you considering? So,
Any, basically.
okay.
Apart from not, the only thing I can't consider is very, very large wavelengths, because then I have to be so far downstream that the boundary layer would take up the entire duct. But apart from that, it can be any.
So you're not past the transition lead?
No. Well, I don't really consider that kind of stuff, because it's all idealized.
Any other questions? Okay, well, thank you, Owen.
Good morning, everybody. My name is Francesco Garita, and today I'm going to talk about predicting and controlling thermoacoustic oscillations by means of low-order models coupled with data simulation. Here is what happens when you put a premix flame inside an empty tube. That's a premix flame made up of ethylene, methane, and air. When you put an empty tube on top of it, you get quite a loud noise. This noise arises because of interaction between the acoustic waves inside the duct and the heat release fluctuations at the flame. The acoustic waves inside the duct are causing the velocity and pressure to oscillate, to fluctuate, and the velocity fluctuations, particularly at the flame holder, are causing the flame itself to fluctuate and to wrinkle, and that causes the heat release to oscillate as well. That's the experimental setup we're currently using at Cambridge. It's basically an electrically heated Ricky tube. When the heater is on, a buoyancy-driven flow sets up. We carry out experiments where we increase by 10 watts the electric power every hour approximately. And we reach powers of 180 watts approximately. So since for these powers the system is stable, what we do is to put a loudspeaker at the bottom of the tube and emit a pulse every minute at a certain frequency, close to the natural frequency of the duct, and for a few milliseconds. And we observe the exponential decay. And through this, we measure the by fitting a line through this decay, we can measure the growth, the decay rate in this case. Also, not shown here, there are many thermocouples placed on the rig through which we measure gas and wall temperatures every 8 seconds. So we've got many experiments. First of all, we model the buoyancy-driven base flow, and to do this, we use the energy equations for the gas and for the solid, which are 2 unsteady coupled PDE, and we use the integral momentum equation as well. Now, these 3 equations depend on 3 parameters: inner Nusselt number, outer Nusselt number, and pressure loss coefficient. And so once we know these 3 parameters, we can advance forward in time our model. The question is how to get to know these 3 parameters and how to include the effect of experimental observation. For this, we basically make use of data simulation. So what we basically do is to advance forward in time our unsteady model and to update our model predictions every time experimental observation become available. So basically every 8 seconds. And to do this, we use an ensemble Kalman filter, which basically identifies the optimal state estimate and its likelihood based on the measurements distribution and on the model prediction distribution, which is reconstructed from the ensemble. The ensemble is basically a set of many simulations which are run with slightly different parameters and initial conditions. In our case, we use an ensemble made up of 30 members, so 30 simulations running in parallel. And we use the filter both for state and parameters estimations, where the state here in this case would be the temperature profile. of gas and of the wall. So every 8 seconds, we update our model for state and parameters estimation. On top of it, we build our acoustics model. And to do this, we use a wave-based approach, which relies on backward and forward traveling waves, which reflect off the boundaries characterized by these two reflection coefficients that we assume to be equal. In the assumption of no mean flow, we derive the linearized acoustics equation with the related jump conditions, and we use the the classical n-tau model, through which we relate the heat release fluctuations at the heater location with velocity fluctuations at the same location, which are delayed by a quantity tau. So n and tau are the parameters of this thermoacoustic model. Solving the linearized acoustics equation leads to solve the following eigenvalue problem, where you basically notice this thing. We model n and tau by means of two parameters, kn and k tau, and also all the quantities that appear in this matrix rely on the base flow model. Why? Because in this matrix, basically, we see the average speed of sound. The reflection coefficient depends also on the average speed of sound and also the inlet velocity, which appears here. So once we know the base flow model, we can actually solve for this equation, nonlinear equation, determinant of this matrix equal to 0. S in this matrix represents the eigenvalue, whose real and imaginary parts are the growth rate and frequency of the oscillations. So once we know Kn and k tau, we are able to solve for this nonlinear equation through the Newton's method, for example, and we can calculate S. But the question is, how do we know Kn and k tau? Well, the answer is that we infer them from regression. We basically have got a large set of eigenvalue problems because we've got a large set of experiments. Each experiment corresponds to one eigenvalue problem. And so the approach we follow to derive Kn and k tau is the following. First of all, we use the Kalman filter, as explained before, for the base flow model to derive the average gas temperature that gives us the average speed of sound inside the duct and the inlet velocity, which is a key parameter here. And then we solve for this minimization function over all the experiments, which are more than 1,000, where the objective function is basically the determinant of the matrix I showed you before, where the eigenvalue S has been replaced by the experimental eigenvalue, which is known from experiments. And so this makes things easier. Once we know the best fit Kn and k tau, we can a posteriori compute the eigenvalue S through the Newton method, for example. And we do this for each experiment, and we compare the obtained model prediction of S with the experimental eigenvalue. These are the results that we got without including data simulations. Here we are plotting growth rate and frequency, so basically the eigenvalue of our model compared to the experimental results. Without including a data simulation means that it means that we basically assume the reasonable stepwise constant profile for the average gas temperature and the inlet velocity, and these are the results that we got. Now the question is, what happens when we basically take into account data simulation? Here is the answer, where you can see that we've got a tremendous improvement in the model prediction of the growth rate. You may notice these large oscillations, but these are just due to the fact that the experimental reflection coefficient slightly fluctuates. And these fluctuations are amplified when solving the nonlinear problem. So in other words, if you take an average reflection coefficient, you wouldn't observe these oscillations, but you will see a smooth curve. So to conclude, what we've done in this work was to try to predict thermoacoustics oscillations by means of a low-order model coupled with data simulation. And the results got so far, at least for the negative growth rates range, look quite promising. So we want to basically, our aim is to extend this work to increase the electric powers and get to the range where we actually see instabilities. So we see positive growth rates. The final goal, in this way, we will be able to characterize the system for this given configuration over an entire range of operating conditions. And the final aim will be then to change the configuration of our system, for example, by changing the heater location, and to see whether we can actually predict the instabilities by keeping the same parameters that will land on this on the same configuration, on the old configuration.
Thank you very much. Any questions?
So in your experiment, what is exactly your heat exchanger?
It's an electric heater, normal control.
So it doesn't affect the fluid?
There are two rings and a grid, a mesh grid, which is heated through a power supply, which is connected to the computer. And we automate everything, so we control everything by the computer. The long run lasts about 20 hours, but you don't need to be there. So.
Any other questions? Okay, another question.
And how is this related to the flame thing that you showed at the beginning?
Because the instability sets up even if you don't have an actual flame. If you have an electric power, this releases basically heat, and this heat interacts with the acoustic waves inside the duct, and the small fluctuation of the heat release basically causes this thermoacoustics instability. So you see the instabilities even if you don't have a flame. You just need some.
Due to the curvature of your flame,
But you don't need it to see this, to hear the noise.
Okay, well, thank you, Francesco.
Thank you.
So, good afternoon. So I'd like to talk about some work investigating active flow control done with my supervisor, Lorna Ayton. So first of all, the general kind of problem that we have is unsteady flows interacting with a body scatter and generate sound. And to make aeroplanes and wind turbines less annoying, we'd like to do something to reduce this noise. So I'd like to talk firstly about how we might be able to use active flow for this purpose, how we can model this using vortex sound, and then really motivate some mixed boundary value problems and kind of related to this and suggest an approach and kind of give you an idea of what kind of problems this approach might work for. So first of all, we could do something passive, like Dave talked about earlier. We could manipulate the geometry, we could, or the materials to reduce the scattering. But this is quite limited as to what we can do. So one thing we could do is to add some energy to the system to allow, and of course it makes implementation more difficult, but it gives us a lot more options with what we can do. So in particular, we could adapt it to the environment, so make it, in principle, kind of create an optimal strategy for an airplane taking off or landing. So one idea is continuous blowing, which was investigated in Bristol by Zoka and Asprand. And they found significant reductions in the surface pressure fluctuations, and so kind of indicating that we might be able to get a reduction, significant reduction in the far-field sound. So just kind of give an outline of how we're going to model this, just to give a very simple kind of intuitive model of how this blowing might work. We consider a 2D potential flow, and we just model our kind of disturbance as a point vortex. And then we can solve for how this vortex moves around a particular geometry, and in particular, if we've got a different background flow, say, due to our active flow device. We can then use this as a source in an acoustic analogy. So we use the total entropy, but it's, we can just think about this as pressure, in effect. And to solve this, we then want a Green's function for this wave equation. But ideally, we want it tailored to the geometry, so you don't have to do any integration over our boundaries. And for a trailing edge, we have a really nice expression for this, using conformal mapping and taking the compact limit due to Howe, where we find that the kind of acoustic signature in the far field, the pressure, if our vortex is at any given location, is dependent upon the geometry through kind of the conformal mapping zeta and the speed at which it goes. And in particular, this is just a function of position, so we can get an idea of a sensitivity map, and we get this idea that kind of sharp edges are bad as far as noise reduction is concerned, and that if our vortex is close to the sharp edge, we get more sound, but if we smooth it with a cylinder, we get a reduction. So we're going to model the active flow by just imposing a normal boundary condition, a normal velocity profile. But the precise profile itself doesn't matter too much. It's really the mass flux, unless the vortex is particularly close to the device. And then in our non-dimensionalization, we have some parameters associated with where we put our device from the edge, this distance L, and the strength of our active flow Q. And also some parameters about where we start our vortex from and how strong it is. So this gives us a nice model that we can see that as the vortex passes, is released from upstream of the active device. As we start to blow, we end up with a new peak due to the vortex interacting with the active flow device. But then we notice a reduction. So we can kind of think about the active flow as blowing the vortex away from this region, particularly sensitive region, so reducing the fluff of sound. So this gives us kind of a nice intuitive model for understanding some of the basic principles at work. One thing we can do is we can then do some optimization. We can look at kind of how this depends upon various things, because fundamentally we're solving a kind of one-dimensional ODE. It's very quick. But this model is kind of quite basic, and so really we'd like a more sophisticated view. And in particular, some problems happen if kind of what happens if we turn this device off. Well, we've now not got a rigid plate in particular. It's more obvious that we don't have a rigid plate. We're blowing out of some section, and so we've got a porous section. But this creates more sharp edges over which we've got scattering, and this is going to affect the far field sound. So how do we start to quantify this? How do we construct an appropriate Green's function? So typically, kind of analytically, we'd kind of reduce this to a matrix Wiener-Hopf problem. But typically, we don't have accurate methods for their solution. So I'd like to kind of explore an iterative approach, which I've been working on implementing, and really kind of go through kind of, as I said, kind of to give you an idea of the kind of problems that this can deal with. So typically, we have our PDE. We'll apply some appropriate transforms to reduce it to an ODE, which we can then solve to find our general solution. And then we want to impose the boundary conditions. And of course, as soon as we get these mixed boundary conditions, we find difficulties because our transforms, we have to split where our junction is. And so in particular, when we start to impose, say, for a semi-infinite rigid plate, we end up with having kind of a functional equation with two unknowns. So we can't kind of solve this directly. This kind of gets worse when we have more junctions. That when we have n junctions, we get n equations, but two n unknowns, in fact. So this is where the Wiener-Hopf technique comes in, that we start to think about equation holding in the complex plane. We then start to notice that our transforms have certain analyticity properties and algebraic growth in different half planes. And then if we start to split our equation, we can kind of, in a similar way to separation of variables, start to think of kind of split it into a function which is analytic and has most algebraic growth in the upper half plane, and similarly for the lower half plane. And then using analytic continuation and Liouville's theorem, say this is equal to a polynomial, and work out what this polynomial is by the edge conditions. So now we've got a way of kind of getting two equations. So matrix Wiener-Hopf problems are slightly more difficult. The way that I'd like to describe kind of one of the difficulties associated with this is in terms of coupling. So say we have a finite rigid plate of length L, then we can form kind of our system from our boundary conditions as two Wiener-Hopf problems coupled by these red terms, which kind of are related to the scattering from the other junction. So, but we can't solve one equation and then the other because we've got the kind of forward and backward coupling. So we can't. But actually, if we think about this problem, and this was what Anastasia Kazil kind of suggested and has been started to be implemented, is let's neglect one of these couplings initially. Basically, this is associated with a backscattering effect, so we think it's initially weaker. And so this is kind of related to this problem of if we know how to solve x equals g of x, we can then construct an effective iterative scheme to solve some perturbation of that problem. And this will converge well if it's small, but in principle it can also work if it's just subdominant. So this is where kind of the work that we're doing currently comes in, is actually automating this numerically means that we can do lots of iterations. which suggests it can be developed to a lot more geometries. And really, this kind of idea of coupling can be extended to kind of the multiple junction couplings that we want for active flow control, but also for a lot of other problems that involve mixed boundary conditions. So in particular, we can see an animation of how it converges, that it kind of corrects for each junction iteratively. And in particular, it converges quite fast, converges exponentially. And in particular, by automating the process a bit more, we can show that it converges for quite low wave numbers. It takes a bit longer, but still fundamentally, we're avoiding inverting a matrix in solving this problem. That in fact, we're using a perturbation expansion to approximation to a matrix inversion, which is chosen effectively by considering these physical couplings. So this provides a basis to consider these more complex, kind of coupled Wiener-Hopf problems. So just to summarize, active flow control gives us some interesting possibilities, and that we've got an intuitive model in vortex sound that's quick, but has quite a lot of deficiencies as far as kind of more sophisticated analysis might want. And so this iterative approach to Wiener-Hopf problems could be a really effective way to construct the Green's functions we require and be an effective approach in kind of mixed boundary value problems more generally in fluids and beyond. So thank you very much.
Thank you very much. Any questions? Well, I've got a question. Your approach involves blowing
yes.
the vortex away, but won't the aerodynamicists object to this? They normally suck in the flow
yes.
to keep the boundary layer under control, which is rather important to them.
Yes, so I think that's, so within the current, it's much easier to model in the vortex sound framework, blowing than suction, suction so that's one question. I think suction, yeah, I think suction is just much more difficult to model using these analytic techniques. I'm not quite aware.
Make it louder,
yeah. Suction,
you're blowing the vortex away to minimise the interaction.
well, you can kind of view it as sucking in the vortex. So it might be possible to do kind of a crude model of making your vortex vanish at some point. So yeah, so they also quite effective, and often you need slightly lower strengths if you do things inclined. But yeah.
Okay. Yes.
Early on, you talked about an experimental work.
Yeah.
Use constant flow.
Yeah.
And you said they showed that the pressure fluctuations went down. But did they do any kind of correlation to any kind of far field predictions? Because otherwise you don't know that the pressure fluctuations might be just hydrodynamic. They won't be acoustic at all.
Yes, I'm not quite sure. So they did. I mean, they didn't measure any far field because it's much harder to measure the far field. Yeah. So yeah, so that would be interesting experimental work. I'm not sure. Yeah, I'm not sure if I'm aware of any that's done blowing and far field sound, but it'd be interesting to think about.
I should say we'll probably hear more about this next year, won't we, at the Isaac Newton Institute, where
yes.
there's a special programme.
Yes, yes. So,
and that applies, I think, to several of the talks we do.
Yeah.
Well, so I'd like to thank all our speakers. So thank you very much.